Hi, welcome back to our parallelism module. Before we introduce the ways how we actually accomplish parallel operation, let's try to establish a baseline. And our baseline will be some common kernel executed on sequential machine that we have studied so far by using programming techniques that are familiar to us. So let's start with matrix multiplication. We have seen matrix multiplication to get a matrix C, which is a product of two matrices A and B. We would walk through over the elements in that matrix C, over all the rows and columns to find the elements C, I, J. And they're going to be element-wise products of corresponding rows and columns in matrices A and B. So for example, to find an element C11 in this matrix, that would be a product of A1, 1, B1, 1 plus A1, 2, B2, 1. When we plug in the numbers for the sample matrix down here, that would be equal to 1 times 1 plus 0 times 2 equals to 1. And so on. We continue doing that over all the elements I, J in the matrix C. When we write a program, this is essentially triple loop. We are going to walk over all the elements I, J, and K in 3 loops. Let's take a look at the implementation in a familiar language like Python. So matrix multiplication in Python essentially implements those 3 loops. We go over the coefficients, we walk coefficients I and J within their range. In this case, these are square matrices. We initialize each of the values for the elements C, I, J to 0, and then we accumulate, in the inner loop, we accumulate A times B from corresponding places in matrices A and B. When we try to time that, we can find out that the result is fairly independent on the size of the matrix. We get about 5 megaflops. What are megaflops? Well, that's a measure of how fast is our computational throughput. You'll often hear people referring to megaflops, and that stands for millions of floating point operations per second. Now, each of the floating point operations here that we encounter is counted separately. So we are going to see a floating point add and a floating point mult. So each add and each mult are going to be 2 separate floating point operations. So there is one floating point operation that corresponds to multiplication and one floating point operation that corresponds to addition. So this line of code is 2 flops. So when you take a look at this, therefore, since this is a triple loop of square matrices of each of a size n, so it takes n cubed flops times 2, because within each iteration we have 2 floating point operations. Now, is this fast or slow? It's kind of hard to tell. I mean, we really haven't discussed that so far. So let's take a look at a second example. Let's see how do we implement this in C language. Well, there is not much difference. In C, we are going to have a scalar, which is our sequential kind of an operation. So here is our dgem scalar baseline. It's a triple loop. Inner element gets initialized, and we accumulate A times B products to it. How long does that take to do? Well, you can actually run this experiment. There is a standard library, time.h, that exists in C that we can invoke. And what we can get from that, we can get clock. So we can get clock cycle when we start running this matrix multiplication, and we can get then clock that corresponds to the end of execution of a program. And if we run the program, we call dgem as a function. In between, we are going to get the number of clock cycles that it takes us to execute. If we divide that by the number of clocks per second, we get the speed of our matrix multiplication. So if we repeat that versus Python and compare it to Python, this is what we get. And numbers here of how many flops do we get is actually in gigaflops, not in megaflops, it's in gigaflops, so in billions of floating point operations per second compared to megaflops that we have seen in with the Python. And we see something kind of surprising. This is way faster. Code running in C is way faster than code running in Python. It's not just a little bit, it's like 240 times faster. That's crazy. You should feel good about yourself now. You know C and you know how to do these things that correspond to performance programming. That's a kind of a big deal. And you can think about, you can start appreciating 61C even more than you are appreciating so far, because there is no other class that gives you 240x boost in your performance programming skills. There is another interesting thing here that we see is that the performance in the numbers of gigaflops is constant until we get to a certain size of a matrix, and then it drops. What do you think? Where does that come from? It has highly likely to do something with the cache size. Some of these things may not be fitting in the cache. Some of these matrices may not be fitting in the cache. So, this is great. We improved the performance by 240x. But we don't want to stop here. We're going to make this matrix multiplication go faster and faster throughout this module. So we're going to take a little break and then talk a little bit about how do we classify these different types of parallelism. See you after a break.